Okay, in this video, we try to answer the questions that was raised as in a form of running slide. Let's assume this is a scheme of electrochemical cell in which this is the zinc electrode and containing zinc salt. Likewise, here the copper electrode and copper salts. When they are connected and under temperature 25 degrees Celsius and 1 molar solution if taken and the pressure is being 1 atmospheric pressure, we term they are in the standard condition. And under the standard condition, this are supposed to produce electrical energy to the maximum of around 1.10 volt. That's a known factor. But now what happens when the same experiment been carried out under non-standard condition? Meaning it is now no longer 1 molar concentration or the temperature is maybe above or below 25 degrees Celsius and the pressure is not the same 1 atmospheric pressure. In those circumstances, how much electricity is produced? That's the question. So let's assume now the same experiment being conducted in a non-standard condition and it of course produces electricity. That's why this bulb glow or lit it out. But how much current can be produced? To know this answer, you have any idea? For this question, one gentleman came forward and he given a relationship, and that relationship is called as Nernst equation, which gives the value. What value? How much of electricity can be produced under the non-standard condition. So actually it relates the electrical energy produced under non-standard condition by comparing the same current produced in the standard condition by adding or altering some values. This is the value. Okay, so this is the relationship. So realistically speaking, this is a relationship that compares the cell potential at a non-standard condition with respect to the standard condition by altering some values. This is the value that been altered. Now, why do we need to understand or how do we believe that the relationship is true? For which we can we need to know who is this Nernst all about. Therefore, now we'll look a shorter glimpse about the Nernst. He is a person born in Poland on 25th June 1864 and he is a Nobel laureate. And that too for the contribution he made in thermochemistry. And therefore, now we can to some extent understand how or we can now appreciate how we ended up with the Nernst equation connecting the thermodynamical parameters in explaining the how much of electricity being produced. That's why he contributed to electrochemistry. Now, having known about Nernst, now will I try to find how this thermodynamical idea that he had just given to understand the electrical energy. We pretty well know that any reactant, if try to give product, why the product being formed? The product being formed because of spending of some energy, and that spending of energy is called as free energy or Gibbs free energy. Meaning this is the amount of energy to be spent by the reactant molecule to yield product. Right? How do you calculate delta G? Delta G can be easily calculated by this relationship. Delta G is equal to delta G naught plus RT ln of Q. What is R? Gas constant. T? Standard temperature 25 degrees Celsius or 298 Kelvin. What about Q? Q is called the reaction quotient. What is reaction quotient? See, when for a reaction like reactant gives products, reaction quotient would be the concentration of the product, ratio of concentration of product to the ratio of the react. That's called reaction quotient, isn't it? Now, this is apply for any chemical reactions. Actually, in this case, the metal ion gaining some electron and becomes metal. Now this is also and also producing electrical energy. Now this is also a sort of a chemical reaction, and therefore very well we can apply delta G is equal to delta G naught plus RT ln of Q. Okay, meaning In this case, for a redox reaction, it is this free energy actually converted itself into the electrical energy. Therefore, by knowing this energy, by knowing this free energy, we'll be able to talk about the electrical energy. So how to calculate this delta energy? It's very simple. Look at here. The delta energy is actually equivalent to the work, isn't it? Delta G is equal to work. What work? The reactant demolishes the bond of being reactant and making another sets of bond only to become product. That's called the work it done. Okay. To do this work, it has to spend energy. That's why it is negative in symbol. என்ன சொல்றோம்? The point is the reactant becoming product. How it becoming product? By demolishing its own bond and making a new bond, isn't it? Now, and now what is the work in case of electrical or electrochemical reactions? It's actually movement of electron. See, we are having one half cell where the oxidation takes place. We do have another half cell where we expect a reduction, and therefore the electrons are being produced are transported via salt bridge as mentioned here. So here the zinc becomes oxidized, releasing these two electron, and this electron jumps to another half cell. So this is the work, transporting the electron to the other end. That's the work. So so how the work can be calculated, or how much energy to do that? That can be simply delta G is equal to n times of n times of f times of E of a cell. NFE cell. What is this N? Number of moles of electron that starts moving from oxidation cell to the reduction cell. What is F? F is a Faraday. That's the amount of electrical energy produced because of movement of 1 mole of electrons. And what is this E cell? E of a cell is actually, I'll write it clearly, delta G is equal to N F N E of a cell. Now what is E of a cell? E of a cell is nothing but the potential difference arising by the difference in the potential of oxidation cell and reduction cell. Correct? Now applying here, I can say that delta G is equal to minus of NFE. Okay, therefore it becomes, substituting in the above equation, it becomes NFE equal to minus of NFE naught plus RT ln of Q, isn't it? Now dividing this equation, okay, now dividing this equation by minus of NF, okay, now by dividing this value, the whole of this equation, upon dividing by NF, that will bring E is equal to E naught plus RT ln Q divided by NF. Okay, so this is called Nernst equation. This Nernst equation can be sometimes be written the other way, such that E is equal to E naught minus of RT by NF into ln. The quotient Q stands for the ratio of concentration of the product towards the concentration of the reactant. So they are one and the same. This is called Nernst equation. But the care must be exercised in using the appropriate symbol. In this case, we use positive unit, whereas in this case, it is used as negative units. I'll explain whether to use plus or minus using a problem. Thank you very much. So, the real Nernst equation can be written as E is equal to E naught plus 0.059 divided by number of moles of electron into log of product by reactant. Now this symbol, the plus or minus, to be well noted. Sometimes it would be minus, sometimes it would be plus, depending on what? Depending on this factor. Okay, so caution must be taken. Now I'm going by this formula, that is product per reactant. Now what's the product and what's the reactant? So it's very obvious that the products are the magnesium ion and your silver. That's your product. What's your reactant? That's the magnesium and the silver ion square. That's your product. Sorry, reactant, right? I repeat. So this is the product and this is the reactant and product, isn't it? Now we apply them directly. Before that, how do you calculate this E naught? Luckily for this in this problem, the E naught value is given, that is 3.17. Sometimes it won't be given. In those circumstances, how will you calculate? See, the cell potential can be easily calculated under standard condition by this formula, E of R. What is this E of R? That is reduction potential of the cathode. According to IUPAC notation, reduction potential of the cathode to be always written in the right side. Therefore, I can say that E of R minus of E of L. By the way, what is E of L? Reduction potential at anode. So when you take this difference, that value must be equal to 3.17, and that's how we obtain. But what values to be referred from where? The reduction potential value for the standard can be under standard condition can be referred from electrochemical series, or it can be otherwise called as standard reduction potential series. From those chart, you will be able to get the reduction potential of your magnesium as well as silver ion under standard condition. By taking the difference, you will be end up at 3.17. Now falling back here, this 3.17 to be added by 0.059 by, what's the value of N? Actually here it's the magnesium metal atom becoming magnesium ion. Therefore it releases 2 electron, and that 2 electron reduces 2 silver ion. Therefore the electron that are obtained are 2. So 2 electrons are moving from anode all the way into the cathode half cell. That's why it is 2 into log of, so these values has to be written over here, but usually we never written solid because they act as a spectator, won't take part in this reaction. Therefore it must be magnesium ion divided by silver ion, but this silver ion being the product, I am changing to the numerator. That's why it becomes plus. Therefore that becomes silver ion is 0.0001 squared divided by that magnesium ion is 0.130. Suppose when you reciprocate the values, that is 0.130 going numerator and 0.0001 coming to the denominator, then the value plus to be turned into the minus, as I said earlier. Okay, since I go by the plus way, I have to write in this order. Please note. Now taking the simplifying these values and taking log, that would come around 3.17 plus 0.059 divided by 2 into minus of 7.1139. Now multiplying these two factors, that will give you 3.17 minus of 0.0298. So the final answer would be 2.960 volt. So this is the electrical energy produced for the mentioned electrochemical cell of the given concentration. Okay, now we come to an end of our discussion.